Okay, thank you. So the Concerto CTD, as we mentioned, both versions have 240 million readings on the memory, and they can all sample up to 32 hertz. They have some configurations such as you can have them sample at fast 8 hertz, fast 16, or fast 32. They all have USB-C for direct download, and then they also can be downloaded through Wi-Fi as well. Another version of the CTD that we have is called the Brevio. This is a little bit shorter than the Concerto. Instead of holding 8 AA batteries inside, it holds 4 AA batteries inside. And again, it can have internal logging, it can be enabled with Wi-Fi, or it can have a direct connect through a cable at the end, which could be used on some vehicles to either control it or to provide feedback to the vehicle itself. Again, it can be configured with fast versions and with deep, so with a titanium housing. So these CTDs are used, as you can imagine, vertical profiling on ships and small boats. It can be used on underwater vehicles. And of course, also for deep projects. So not only deep profiling, but also deep moorings. This is a photo of the British Antarctic Survey from the UK deploying some CTDs and inductive modems through 700 meters of ice before they go into the water. And there's a nice paper that's available on the RBR website, but also linked here if you decide to download this PowerPoint after the presentation. You can read this paper. It's about an RBR CTD, 2,000 meter CTD deployed next to a Seabird CTD in Antarctica for about a year. It was just recovered this summer in Antarctica, so about 6 months ago, and the data has just been published recently. Also, there are some visitors that we get when people are using the CTDs for vertical profiling in Antarctica. This is actually a photo that Brittany's team shared, and so maybe we'll see more of these cute fellows later on. In terms of deployment configurations, we can see that the RBR CTD, when sampling at 16 hertz continuously, it will actually have enough memory and power to run for 38 days continuous sampling at 16 hertz. That means essentially, if you want to sample at 16 hertz during the working hours, you could go almost all summer without having to ever change the batteries. Or if you deploy it on mooring lines and say, for example, instead of sampling continuously at 16 hertz, you sample at once every 10 seconds, there's enough memory to last, enough memory and batteries to last for 3 years. So that's making a measurement every 10 seconds on a mooring line, and you can deploy it for 3 years. And this is common how people will deploy it, maybe making a measurement every 10 seconds for a 2-year project, but then they have 1 year extra battery just in case the ship's delayed or they can't get on site the year that they intend to go. Now we're going to move a little bit into the Legato. So the RBRlegato CTD is what we make for underwater vehicles, and it's simply an evolution from the standard RBR CTD that people have known and trusted for a long time. The Legato means, the word means smooth, connected, and carefully integrated, typically referring to music, but we like to refer to it as this product. And it comes in 2 versions. We have a wet bay version, which is used on vehicles and platforms that have a flooded section where water is expected to be on all sides of the instrument. You can see this is fully waterproof with an underwater connector. And then we have the dry bay version, which is used on a couple of gliders where it's expected to be dry inside and you don't need a bottom covering to protect the electronics. As we said, the CTD is really just an evolution of the normal CTD. So we have the normal inductive conductivity cell, the normal thermistor, and the normal pressure sensor. And the size is made to fit inside the standard Seabird glider payload CTD, or the GP CTD bay. It's rated to 1,000 meters. The standard sample rate is 2 hertz, but we can upgrade it to 16 hertz, and we can put a fast thermistor with a 100 millisecond response time if you want to sample faster. The system doesn't need a pump. It's naturally flushing, and it's very low power. It's only about 1/10 the amount of power, 18 millijoules per sample, compared to the GP CTD, but it has the same accuracy. Some of the opportunities that this provides for people: first, lower power means greatly extended missions. If you're on a glider, you can now sample on the descent and ascent because you've got so much more power available. You can get improved measurements through gradients and strong thermoclines. Because the temperature sensor is co-located with the conductivity cell, there's a very short lag, and we provide some post-processing tools in RSK Tools, which is a MATLAB toolbox for free that can help you align and remove that lag. Finally, the wet-bay system is connected with a wet pluggable connector. This means that the user can remove it very easily. You can send it back to RBR and get a quick calibration. You don't need to spend a lot of time in engineering removing things, changing O-rings, and inspecting it. Finally, because it's silent, which means there's no pump whatsoever, it's quiet, and this is useful for improving passive acoustic measurements where you're trying to listen, and also turbulence studies where you're trying to measure very small vibrations of the ocean, and you don't have to deal with vibrations of the pump itself. Finally, all of the legatos, just like all of the CTDs, can function as what we call a sensor hub. This means that the legato can easily integrate with other sensors, such as an oxygen sensor, maybe turbidity sensor, a fluorometer. The legato will manage the sampling and power of those, and you just get one data stream fed in. So you don't need to plug lots of things into your underwater platforms. You just plug in the legato and it manages the rest of it. So the legato has been integrated on most of the gliders. This is a photo on the left of Rutgers deploying one of their G3 Slocum gliders off the Mid-Atlantic Bight off New Jersey. You can see the legato is tucked in the normal GP CTD bay underneath one of the wings. And here's an Alcimar glider where the legato is flush in the nose cone. And Alcimar is using legatos widely when they are doing acoustic sampling with a hydrophone because they appreciate it being quiet and low power. And here we have a photo from Applied Physics Lab at University of Washington with legato integrated into the wet bay section of the Sea Glider. This was made by University of Washington, now commercially available by Hydroid. Here they have a hydrophone as well, and they ran this mission in Guam at the end of 2019 and into the beginning of 2020. We do have webinars every week. The next webinar we want to alert you to is next week, same time, same place. This one is by one of my favorite people, Glenn Garkowitz at Hui, talking about some collaboration that Hui's done with fishermen, commercial fishermen off of Rhode Island, and how not only how Hui is using the scientific quality data for their own research, but how the fishermen are actually making better informed decisions by making temperature and salinity measurements all the way to the bottom. Okay, that's my section over. I think you all tuned in to hear Brittany and her team, which is really great. I did want to make two quick mentions. One is that RBR records these videos. So we do that so that if you want to watch it and then not have to take notes, you can watch it later to catch anything you missed. You can also use it, you can also forward it to your colleagues that might be interested that didn't receive it or didn't get to watch it in real life. The second is that we encourage questions. You can use the chat section of Zoom, and you can write your questions in while the speaker is speaking. Some of the RBR staff will be on hand to try to answer them. If any of the folks from Georgia Tech are available to answer it in real time, of course, we welcome that. And finally, at the end of the webinar, we will open it up for real questions. Then you can type in your questions as well, or you can get on the Zoom audio or video and ask your question, and we'll all try to address it. Okay, so that's it for me. What I would like to do, I'm going to stop sharing here. I'd like to introduce Brittany and her team to come online. Maybe share the first screen, Justin, and while we're doing that, while you're getting that set up, I will ask Brittany. We'd usually do a short interview with Brittany, so I'll ask you, Brittany, first, can you give us a little bit of an introduction about your background and maybe how you were specifically contributing to this Icefin project in Antarctica?
Certainly, yeah, sorry, I was trying to figure out why I wasn't showing up, and it's because I still had tape over my camera. So hi, everybody. Yeah, sorry. So we kind of got started in this project. My original interests in Antarctica were actually as comparisons for planetary exploration. So my background's as a planetary scientist, and we're really do a lot of our work also on understanding the moons of the outer solar system. So these places with thick ice shells and ice ocean processes that we as yet are just hypothesizing. And so that's kind of the background for the work that we got started doing. And we started developing Icefin when I got to Georgia Tech in 2013. And so Icefin's the vehicle you're seeing here. And we're going to kind of present some of the history of using the sensors around Antarctica. We have a kind of a non-traditional approach to doing things, and so we'll have a non-traditional approach to doing a talk. So I'd like to introduce the other folks from Georgia Tech. So Justin Lawrence is a PhD student in the lab, has done a huge amount of work on Icefin and the sensor development and pipelines and everything. Peter Washam is a postdoc in the lab, who has also kind of been our resident oceanographer. For most of us, we're kind of coming at oceanography as a newer field. And so it's been really great to have Peter around as well, and he's been a fantastic asset. And then also Matt Meister, who is our lead Icefin engineer. So Matt and I have been working together since 2014 to develop Icefin and all of the other crazy things that we try to do. And so it's really a pleasure to be talking with all of you today.
Excellent, thanks. And as is history on these and tradition on these webinars, we also ask for you to tell us one fun fact about yourself that the audience may not know. Maybe even some of your team don't know, but I don't know how. It seems like you've been working with them for 6 years, so I'm not sure how much is private now.
Yeah, when you live in a tent with people, that's not, there's not a whole lot they don't know. I was trying to think about something that would be funny, and I guess since we're all like living in our houses and cooking all the time, I decided to feature the fact that I'm obsessed with rosemary. I pretty much put it in everything, probably at a level that most people are uncomfortable with.
Okay, I like that. I like that. You could test me. I don't think I'd be uncomfortable with rosemary. I'm pretty content with it. Okay, I'm gonna let you go, but I wanna say, or let you get started, but I wanna say 3 things that we've really found, the RBR team's really found about why we like working with your team. First, of course, you do really good science, and that's really critical. Second, you've got, as you mentioned, a non-traditional and very creative and innovative spirit, both in terms of the engineering and the measurements. But third, and you can decide how important it is in terms of priority, you folks send us postcards from Antarctica, and we really like that. So, you folks are big favorites at RBR, and I'll let you take it away. I'm very interested in hearing your presentation. Thank you.
Yeah, it's really fun. So, so Justin's going to play this video here. So this is Icefin swimming around underneath the sea ice in McMurdo. So our, most traditional field site is probably the least traditional for most folks' use. So you can get kind of a perspective on the system that we're looking at here. So under here, we're under about 2 or 3 meters of sea ice here outside of McMurdo Sound, Antarctica. So if you go to the next slide. So if you're not as familiar with Antarctica, here are the 3 places we're going to talk about a little bit in the talk. Mostly we're going to talk about McMurdo Ice Shelf, not only because of its fantastic pizza, but because that's where we've been really working since 2012. So my first season in Antarctica was in 2010 as part of an airborne geophysics platform. So we were looking then at using radars that are now on spacecraft that are soon to be headed to Europa as planetary instruments. And then my interest in the ice-ocean interactions kind of started there as being a measurable, kind of measurable processes that we should be thinking about for our planet and others. So we also work under the Ross Ice Shelf. We've been working there with Antarctica, New Zealand, at the grounding zone of the Cam ice stream. We're really excited to be taking Legato out there, hopefully next year. Fieldwork this year has officially been canceled, but that's kind of a long look ahead at what we'll be doing next. And then this past season, though we didn't have an RBR out there, we were also working with our colleagues at the British Antarctic Survey and the International Thwaites Glacier program out at Thwaites Glacier. And we'll kind of show you the use case there for grounding zones just a little bit, just from some videos the team has previously put out. So if you go to the next slide. So the real interest, of course, from an Earth perspective is is understanding to the degrees to which Antarctica is changing and the influence that humans are having on that, as well as trying to constrain just what we should be prepared for. So this shot is satellite image of the Thwaites Glacier, which used to have a very prominent ice shelf that extended well into this ocean that you can now see. It's pretty easy to see what's happening here. Even if you're not an expert, you can see that this ice shelf is rapidly disintegrating. It's being actively melted. So there's warm water that's coming up onto the continental margin and undercutting the ice shelves here. And so those processes are really key to understanding the now accelerating influence that Antarctica is having on global sea level rise. And so when we think about bringing it back to our planet, this is kind of the picture that always fills my head. So next slide, please. So this is where we do most of our work. So this is a view of McMurdo Station, and you can see a couple of interesting things here. You can see the McMurdo ice shelf in the background. There's this light transition you can see right there. That's actually the ice shelf road, I'm pretty sure. But back here is the ice shelf. We've worked through this ice shelf. It varies from about 15 meters thick to 150 or 200 meters thick. And then this region in here is the sea ice that we mostly have operated on. We've lived in a number of these brown modular buildings, and we work in this lab right down here. So that's kind of our view of town. We're going to miss it this year, but looking forward to getting back there next year. And just for reference as well, we work with the Antarctic New Zealand program, which has its station just over the corner. You can't quite see. So next slide. So this is our kind of our perspective on where we've put RBR CTDs in the local area. So we've been working through 2 different programs, and then we also did our test work for the ITGC program this year, also out of McMurdo. So McMurdo is located right here on the peninsula, and so then basically this little curvature here is the thick sea ice. And we'll drive out along here, drill holes, drive out here. We worked underneath the Erebus Glacier tongue at Evans Ice Wall and Barn Glacier. The image that you saw in the promotion for this was actually us putting the RBR through a sea ice crack near Barn Glacier. So this is just the context for the area that we've done the most work, and the Ross Ice Shelf is back out over here. Next slide. So little time scale of our work with RBRs. So in 2012, actually, I was a research scientist, a postdoc, just starting at University of Texas, and the first instrument that I ever bought was an RBR CTD. So we bought the V1 of the concerto as our profiler and logger for a project we were working on at the time. We have nicknamed this Cassini. We think of it as our flagship instrument of our lab because it is the instrument that we did most of the science with for the first 5 years of the program. In 2017, we brought Icefin along for its first major Antarctic season. It had been previously tested, and we'd worked with the RBR on a couple of different vehicles, also using the pipelines that'll be described a little bit later for using the RBR as a baseline for correcting some of our CTD measurements. And then we started working really with Icefin in its first major season in 2017. So I joined the faculty at Georgia Tech in 2013 and started immediately building Icefin. In 2018, we upgraded to the Concerto, the V3, so the titanium version, so that we can go the full depth of the ocean water that we find in the McMurdo Sound. And so we've been able to use that kind of all over the place. That instrument also went out and did our calibration work out at the grounding zone of Cam Ice Stream this past season. And then we're really excited to be integrating the Legato into Icefin as its new primary CTD, a long-term dream for the coming field season. So we're planning to go back out to the grounding zone of the Ross Ice Shelf in 2021. So next slide, please. So we're going to talk just through a couple of use cases, show you some pictures of us using the RBRs in a bunch of different ways. We're generally profiling in areas that go up to about 800 or 900 meters in the McMurdo Sound. We use them both to understand how the ocean is changing from dive to dive, and also just over time in general, so we can learn a lot about the influx of warm water coming from the open ocean. And very importantly, we focus a lot on the supercooling and the outwash of frazzle ice that's coming out from underneath the ice shelf. So it's a really interesting ice shelf ocean interaction process that drives the formation of ice actually in the water column, which is a real challenge for CTDs to operate in. We have done some ROV-based surveys. So the first use of the RBR was actually as a tow package on the ROV Skinny in 2012, and we used it also to do some ocean profiling there. And then we also used it in the 2015 seasons, or 2014 and 2015 seasons on that vehicle, and as well as calibrating other data. We calibrate our vehicle data using the RBR standard because most folks are using Seabirds or RBRs, and it's really been nice to see a lot of comparison work being done to kind of prove that both systems work even in the polar setting. And then Justin will talk a little bit about the work he's done to use the RBR to identify individual water masses that we can then sample for biological assays. So we're studying the evolution of the communities in the McMurdo Sound and under the ice shelves, and we're doing that by first selecting where we're sampling using the RBR. So next slide, please. So just a little bit about unique challenges of using these CTDs, any CTD in Antarctica. There's this, as I mentioned, there's this process of frazzle and marine ice accretion, which basically is the water the ocean water right at the freezing point can cause nucleation of ice crystals in the water column. And so those can really mess with your sensors, and it's incredibly difficult to measure because we're actually measuring water that's below its in situ freezing point. So that ice crystal formation affects everything from how the CTDs operate to how the vehicles operate. It affects our design process. It affects how we think about the data as well. So we're working with a couple of colleagues, and we wanted to highlight their work as well. So Natalie Robinson's done a tremendous amount of work in the McMurdo Sound to kind of show various sensors, Seabirds and RBRs, and how they're performing in the environment, and also considerations that we should all take for measuring oceanographic properties in supercooled water. We're also working with Inga Smith at the University of Otago, who's leading a Marsden project that's actually looking at some novel ways to be able to measure supercooling in the water column. So that's kind of the physical processes that we're really interested in. From a planetary perspective, that also drives ice accretion on planets, most likely. So it's a process that we really have a lot of interest in understanding better. Next slide. So at this point in time, we're going to kind of transfer speakers, and Justin is going to give us a little bit of information about some of our use cases under the ice.
Yeah, hi. As Brittany said, I'm Justin, one of Brittany's PhD students. I do a lot of work with Icefin instrumentation, as well as just sort of general water profiling, and then some of the biogeochemical work that we're doing to try to understand these ecosystems and how they operate under ice and sort of how extensive they might be. And then those are lessons that we're trying to apply to other oceans and other places in our ocean. So yeah, I'll start with some of our sort of simpler operations under ice where we do profiling, and then I'll hand it over to Matt after a few slides, and he'll talk a little bit about the vehicle itself. So moving forward, Brittany mentioned supercooling. There's probably some folks on the call who are familiar, but briefly, to get supercooled water, you essentially need ice that is very deep, has deep draft, that's interacting with other marine water. So if you, at the surface, at a Columbia, start forming sea ice, that sea ice formation is going to reject brine, and that makes that water dense. That water will sink down and then circulate, carrying heat from the surface. It's relatively warm down to the base of an ice shelf. Importantly, as most of us know, the freezing point of water is pressure dependent. So as you compress it, you have to do effectively more work to freeze it because water wants to expand as it freezes. And so down at depth, say 1,000 meters or 2,000 meters, where you can actually get ice thicknesses interacting with the ocean in Antarctica at those depths, you can significantly depress the freezing point. So the water that forms at the surface freezing point is relatively quite warm compared to the freezing point down at depth here. And so that ice melts, and as that melts, you get the reverse process in fresh water. That freshwater flux from the melt will increase the buoyancy of that parcel of water, and it begins to rise, and then you go through the reverse process. And as that water rises, it becomes relatively supercooled as it depressurizes and you form frazzle to relieve that supercooling. And that frazzle ice can accrete at the base of the ice shelf and crevasses and all sorts of places and forms this upper water layer. So what does that actually look like? Here's a brief video clip below McMurdo ice shelf showing frazzle and now platelet ice, which are these sort of centimeter scale. And here's a small amphipod for scale as well, below the ice shelf. And these layers can be meters to tens of meters thick in McMurdo Sound, and marine ice accretions can be hundreds of meters thick below other ice shelves in Antarctica. So it's a really interesting environment to work. It's not the typical smooth ice base that we see in some other places. But on to profiling. So in Antarctica, as with many of our field sites, you get unique challenges and opportunities. So here's some shots from Brittany, myself, and another researcher that we work with, Jade Lawrence, in the background here, who we go out and we'll do water sampling and profiling out at some of the field sites that we want to sort of pre-select for Icefin. For example, here we have Erebus volcano and then Erebus glacier tongue kind of coming off the continent here, which is a really unique glacier that's about 10 or 11 kilometers long, but only maybe a kilometer or two wide. And so that we've done a lot of work out there with Icefin. So here you can see we've got kind of a sled, cargo strap, drill, winch situation to do the CTD deployments here, about 100, 200 meters of water. Here's Brittany. Well, here on the left side, we're also doing some ice coring, but also casting with the original concerto that we had back in, I think this was 2017. We've also got some ice scoops modified from, I think these are Canadian made actually as well. So we depend on a lot of Canadian technology, these ice scoops from hockey sticks from some ice fishermen up there. You can do it a little bit easier if you don't have to drill your own hole. This is Tegan and myself. It's a fun photo. You can just opportunistically cast. You can attach a pulley just to the side of your snow machine and throw the CTD through a crack. And that's kind of a really easy way to put a transect in and look at how water masses are evolving as you go from the near shore to the deeper environment and that sort of deeper channel that's funneling water underneath the ice shelf. So that's definitely the preferred method. You don't even have to get the drill out. Sometimes we even get some help. So this is me on the left. I'm actually taking water samples. So this bottle here is a Niskin bottle. I'm collecting some samples here to do DNA sequencing on, take a look at the microbial community and look at some of that really kind of quick cut data. But every once in a while with L seals, we have to share the hole. So we'll put the CTD down, we'll put the bottle through, trigger it, pull it up, and then the seal will be like, all right, that's probably a good time to come take a breath. And so I think this is Patches, who hung out with us for a while. Most seasons we'll have a resident seal, and it's fine as long as they don't get actually up into the structure here, which is our fish hut, which is a small diesel heated hut, because they can make a bit of a mess, as you might imagine. All right, so here's some data from a typical McMurdo Sound water column. This data is down to about 550 meters. It's actually right from the spot we were just looking at where that fish hut was, just off the coast there. Essentially, the two water masses that we work with in the spring and early summer in Antarctica is ice shelf water, or ISW, which is below the surface freezing point, so it's conservatively supercooled. And that means that it's essentially, it's interacted, or some component of that water mass has interacted with ice at some point in its history. And then there's high salinity shelf water, and this is that basically the product of a polynya. So this is that brine-enhanced water that is left over after sea ice forms, that's dense and sinks down to the bottom. So this is sort of filling the deeper waters of McMurdo Sound, and then goes in and ventilates the Ross ice shelf cavity. Also drives a lot of basal melt in the Ross ice shelf. We can do those casts over time, of course, make a nice contour plot, and look at the evolution of that ice shelf water, this blue layer up here that's supercooled, and look at how things thicken and thin over time. And that kind of helps us understand the magnitude of supercooling. And then from a practical application, just helps us plan missions so that we make sure that we know how long we spend in this environment, or we leave an instrument deployed in the supercooled layer, how thick it is and how supercooled it is, tells us, you know, how long until it accretes enough ice to actually float up into the bottom of the ice shelf. And there's been people in the past have lost instruments and even moorings this way as they accrete ice and just become part of the ice shelf. They become positively buoyant, float up even with tens to hundreds of kilograms of ballast. So here's some more profiles, and just talking a little bit about how, you can't really do water sampling without a CTD, of course. So we use the CTD to target the depth of supercooling, and then pick where we want to sample to compare what kind of microbes live in supercooled water to what's sort of living in the open ocean-derived high salinity shelf water down deep. And then we can put that comparison together. This is a quick plot that basically shows the different classes of microbes that we have, and what microbial or metabolisms that they use, and how they support the ecosystems from sort of the ground up. So we see that there's a lot of nitrous homolysis, which is a ammonia oxidizing tau marchiota that supports some of the organic material cycling in subglacial environments. And you can see the different distributions in some of the Corellia, which is a colder water adapted genus, versus in the ice shelf water versus the high salinity shelf water that's relatively warm and interacts with less ice. And so there's some interesting work we can do here, which is of course enabled by CTDs. So moving on to the Icefin section, I think I'll hand it over to Matt Meister, Icefin's lead engineer and a mechanical engineer by trade.
Hey everyone. Like Justin and Brittany said, and sorry, I don't have a camera on my new work computer, so you just get my voice. But like I said, I'm a lead engineer for Icefin and kind of all the various projects we do in our lab now. We've evolved from Icefin to some smaller vehicles that we're working on, and potentially some deeper vehicles. So we have a whopping 6 years of experience, or 7 years. So anyway, talking about Icefin, this is sort of the everything view of the vehicle. The CAD models, they change all the time, and so this is a little bit dated, the main vehicle, but basically you can see in its current configuration, it's rated for 1,000 meters, 3.5 meters long, 24-ish centimeters in diameter, about 110 kilos, and really our range is limited by our fiber optic cable that we use to transfer data back and forth live, but also to recover the vehicle with the Kevlar jacket. And really the big driver, there's two big drivers for its form factor. One, boreholes are typically in the 30 centimeter range, so we needed to be able to fit through that hole. And 24 centimeters was kind of the sweet spot with what we could get with off-the-shelf sensors, and how small we could make things to actually be able to float the vehicle. And then the other reason is we need to take it from place to place. It's already hard enough to do field work in pretty accessible locations, and it's even more difficult to get things down to Antarctica. So Icefin and everything except for the winches actually breaks down into Pelican cases, and we check it all the way from Atlanta down to New Zealand, and then we hop on our cargo flight to the ice, and it's really, really convenient to be able to do things in Antarctica, but also around the world. And so you can see here, these are just two of the, I guess, crucial science and instrument payloads in the vehicle. We have the nose, which is pretty much loaded with all of our sensors that need clean water flow and obstacle detection. So we recently switched over to the Oculus sonar systems, which has been phenomenal. Currently on there now is the Neil Brown CT sensor. And like Brittany mentioned, we're going to be moving towards the Legato here next year. There's a dissolved oxygen sensor. Thank you, Justin. And the dissolved oxygen and the CT are both in the same line, so that we can kind of correlate all of our measurements as close as possible. And then we have two cameras now, one at 12 o'clock and 6 o'clock looking at the nose, and then two lights, port and starboard, so that we can get a view of the underside of the ice and the seafloor, depending on how we do our missions, or if we're in these really tight spaces, we can actually see everything around us. We'll go through the rest of the modules in a second, but then the third module you can see there is sort of our main science module. And this is really where Icefin stands out from a lot of other vehicles. That module can be swapped between the different Icefins. We have two of them now, but also different sensors that we have in the lab. So in the image you can see there, we have a side scan sonar, and then underneath, it's kind of hard to see, there's a Turner CDOM, FDOM, and turbidity sensor, as well as a pH sensor. We've recently integrated a multi-beam sonar. We're thinking about integrating some water sampling, some supercooling instruments. So really that's kind of what makes Icefin stand out is we're able to swap out this one section on the same vehicle between dives. And so rather than, cramming 100 instruments on one vehicle and making it the size of a Suburban, you can make it really small, torpedo shaped, but be able to survey the same thing over and over in a pretty small form factor. So if you go to the next slide, this is what Icefin looks like. This is an image grabbed from this past season. Some of the McMurdo divers were doing some maintenance and they just happened to bring their camera and there was this vehicle swimming around them. So we were lucky enough to get a few awesome pictures. It's kind of weird, but we don't normally get a lot of pictures of the vehicle itself under the water. So that was really cool for us to see this year. If you go to the next slide. And this is kind of a more, it's a side profile view of the vehicle. Like I said before, starting from the front, there's a forward science section. And then the second module and the second to last module are our directional thrusters. So we have 2 vertical and 2 horizontal. So that gives us the ability to station keep, which is, again, one of the unique features about Icefin. It's kind of more in the AUV category as far as its shape, but it can do a lot of ROV capabilities with the hovering and station keeping, which is pretty critical because basically every dive we do is new and we don't know what we're going to find. And so it's really hard to just say, hey, let's do a lawnmower pattern, and then, we'll go back and look at the data and try to get back to the same interesting spot. It's much more convenient to be like, hey, here's something cool, let's stop, let's investigate. If it's really interesting, we'll make a note, come back on the next dive, and if not, we can keep going. Next is that science payload, and you can see in here, this is that multi-beam sonar from Norbit that we've been using. They took it out to Thwaites this year. From what I've seen, it's pretty awesome, and I know all the scientists are pretty excited about that, so that's pretty cool. Next is the big black pressure vessel, and this is the only sealed section in Icefin, and this has probably gone through the most evolution over the years, just with changing computer technologies and batteries. But everything to control the vehicle is inside this pressure vessel. It's about a meter long, and there's 20 lithium batteries, onboard computer, power control, internal sensors to monitor the instruments themselves, the instruments within the pressure vessel, and then all of our fiber optic muxing to send all the signals to the surface. And we also have the ability to do some autonomous control. We're sort of working through those levels of autonomy from, okay, just go in a straight line. Now let's make some turns. Let's make some more turns to eventually, hopefully we can cut the cord here pretty soon and do fully autonomous missions. Probably not under the ice since we use the cable for recovering the vehicle, but potentially, with some future base station work, that might be something we can do. After the pressure vessel, we have our navigation payload, and in here, and you can kind of see below it, from the front, there's an HD camera, and then 2 lasers per scale. They're spaced, I believe, 5 centimeters apart. And then on the far end of that module is also a light, 10,000 lumens for that camera. And that's like our high definition imaging system, which is pretty cool. We get a lot of good video and stills. We're still working through some things there. And then right behind that, we have a Doppler velocity logger with integrated ADCP from LinkQuest. It's also been phenomenal. And then facing up is a altimeter. And with the DVL and the altimeter, we have about 200 meters of range to track top and bottom. And what's also cool about this module, unlike the other ones, this one is basically neutrally buoyant down the center. So you can actually rotate it 180 degrees. And so if you want to track the bottom of the ice with a DVL and get HC imaging of that, you have that ability, and it's just as simple as loosening some brackets and turning the module. Then our other thruster, rim thruster module, and then finally our main thruster in the back. It's a Technodine product. We use a lot of them. It's been great. We can do about 0.4 meters per second with Icefin. It just really starts to slow down when you get a lot of tether drag out there. And then you can see the bottom. Over the last couple of years, we've done between the 2 vehicles over 175 hours, 41 missions, a couple ice shelves, some sea ice areas, multiple grounding zones, lots of very scary areas that vehicles probably shouldn't be going into. And the next slide. And then this is basically all of the instruments that we currently have kind of just organized in electrochemical, optical, imaging, and sonars. And like I said before, we have the ability to basically swap out all of these with new ones, or you know, replace them without a whole lot of hassle because of Icefin's modularity, which is really unique and allows us to do a lot of cool science. And then the next slide. This is what a normal field site looks like for Icefin. So this is right near Erebus Glacier Tongue. I think this was 2017. Basically, we have 2 piston bullies. Those are the red track vehicles. That's what we load all of our gear in every morning or every other morning. We have a couple sleds. Some have winches, some have generators. And the other ones are carrying some more equipment. You can see the large ladder. That's sort of our A-frame that we use for deploying the vehicle. That also has gone through some iterations over the year. But you can kind of see, you know, just for scale, how big some of these things are. All of it breaks down, and we can move it around the ice shelf. And then we operate the vehicle out of the Arctic oven, which is not so oven-like, very deceiving. But that's where we have our base station set up during a mission. And I think I will hand it back over to Brittany.
Sure. So we're just kind of showing setup of the vehicle here. So we've got a couple time lapses just to show what a typical day looks like. We drive out, as Matt said, we put the vehicle together, drop it down the hole, and go off underneath the ice. So these are interesting days because it requires us, you know, usually loading around 7:30, 8 o'clock in the morning, getting out. So to this site here, it takes about 3 hours, between 2 and 3 hours to drive out there. Then you got probably 2 hours of setup. And so then after an 8-hour workday, you're ready to start your mission, which can go another 6 or 8 hours, and then we drive back. So here's a couple of other views of our typical workday. There's Justin and Peter putting in the drill hole, and then launching the vehicle with the team there. So next slide. This is what it looks like inside, the inside and outside of our operations center. So inside you might see some, still some cold weather gear, but the occasional sleeve rolled up. And then on the outside, you might be standing outside in your full gear with wind blowing around you and filling the winch with snow. So what we're looking at here are the topside computers. So we're communicating to Icefin over this long yellow tether. And so we're able to see live what's happening underneath the ice. All of these different readouts here are sensor values. So onboard science sensors or velocity or other things that we're keeping an eye on as we go through a mission. And then we've got our directions, so we're able to see the heading, and our mission plan is down here. So here's Andy driving the vehicle, Ben in the co-pilot position, Matt's in the mission director position, and this is Anthony Spears, our lead software engineer here too. So next slide, please. So this is some shots from us at Thwaites Glacier. This is Dan, our lead electrical engineer, getting some things set up for our mission. Somewhat colder in the tents, as we mentioned. I'm very happy in this picture that the Icefin is returning back up after our first dive, and in the right-hand side is the basically the action shot of when we drove the vehicle right to the grounding zone of Thwaites Glacier. So next slide, please. Just a couple shots of the different teams. So there's our full Icefin team that was there in last season in 2019, and then the team that took out Icefin and the RBR sensor out to the CAM ice stream is there on the right. So that's in the Antarctic New Zealand big tent where the hot water drill happens. Next slide. Here you can see a little bit of what it's like to be Icefin, or what it's like to be the RBR going through 600 meters of ice. So our iced fin picture, and then the RBR here preparing to go down to do some water sampling and profiling of the water column underneath Cam Ice Stream. So next slide. So we'll kind of show you a little bit about some of the work. I think Peter might take over now to talk a little bit about the pipeline processing.
Right, thank you. As sort of has been alluded to previously, it's difficult to collect good data in these environments, and it requires a lot of post-processing. So I'm just going to kind of walk through what we do first with our RBR instruments, and then what we do with the vehicle, and how currently the vehicle is very much married to our RBR. So here in this figure on the left, I'm just showing the post-processing routine. So the furthest left panel is a profile, a vertical profile of conductivity. And despite the one to the right saying that it's a vertical of pressure versus pressure, it's actually temperature. So that's a mistake of mine. But what you see here is basically the evolution of the post-processing that currently we do sort of a custom post-processing that I designed after that 2017 report that was released. This was before RBR had their post-processing software. I haven't tried the new software yet, but I am interested to use it, because right now I'm just sort of walking through all of these steps in a custom post-processing script. But anyway, so this is just an example of a vertical profile, first of unprocessed conductivity and temperature, which is in this blue, and then, you know, there's something like 1, 2, 3, 4, 5, 6, 7 steps, something like that, to get it to the post-process version. And on the right here are the derived variables and absolute salinity and conservative temperature. So the water is very cold in McMurdo Sound, which is why you have in situ freezing. You see the warmest water that we're seeing here is somewhere around minus 1.92. So it's very cold in McMurdo Sound. Justin, you can move me forward now. So moving forward, here's sort of an example of how we use the RBR CTD to cross-calibrate with the vehicle's CTD. So this panel figure are sort of these several panels on the right show an example of some sort of corrections that we're applying to our instruments from the RBR. So this uppermost panel, it says ISO 3-011 McMurdo Sound. That is a mission profile from McMurdo Sound. The vehicle depth over time is shown in black, and then below that is the time series of the vehicle's temperature recorded, or sorry, the ocean's temperature recorded by the vehicle on both an onboard CTD and a DO instrument, dissolved oxygen, that also has a temperature sensor. And then below that is the conductivity over time. So basically what we do during these profiles is, and this has been cut out, but what we do is we send the vehicle down and we soak it first at a depth where it's no longer supercooled, and then we bring it back up. We do the same thing with our independent RBR CTD profiles. But after soaking it, we bring it back up, and then we start this mission. And then the tricky part is basically to find that part of the water column where ideally it would be a mixed layer where you have constant temperature and salinity, but that's not always the case. So here on the right, I'm showing the profiles, the vertical profiles in this red box of the sensors on the vehicle and as NBDO and then the RBR. And this is the uncorrected versions on top and then the corrected versions on the bottom. And what we found is that a constant offset works the best. And we've tested all sorts of things with linear regressions and whatnot. But constant offset is doing a pretty good job. So the figures on the right show we have 2 Icefin vehicles, and this past season we used one ISO 2, which was the one that went to CAM iStream and was in McMurdo, and then ISO 3, which was the one at Thwaites. And this is just an example of the offsets and root mean square residuals after applying the offsets over time. So ISO 3 did really well. The first few dives with ISO 2 and McMurdo, the conductivity was struggling, and I think that was probably due to ice being in the sensor. So yeah, there's oftentimes a lot of post-processing that goes into this to get good data. So Justin, you can move me along to the next slide now. Okay, so here's a little more of the post-processing that now goes into the vehicle. So after we've applied this offset to the data, this is sort of how we move forward. So there's a lot of data recorded during a single dive with Icefin. And Icefin moves relatively slowly through the water column. So currently what we're doing is subsampling all of our physical oceanographic measurements to about 1 hertz. So the steps here are sort of to subsample the data to 1 hertz. And then the following corrections are for conductivity and temperature. And I believe this is applied to dissolved oxygen as well. And what you see here is an example of the first sort of readout from a dive as it begins to enter the post-processing sort of script. So what you have on top is the vehicle track just in Earth coordinates and Latin long. And then you have an example of sort of a 2D transect from the vehicle, and it's shaded by temperature, conductivity, dissolved oxygen, and velocity, with gray being the ice and then brown being the seafloor from this dive. So at the end, what's interesting is that oftentimes we find signals during these dives that require us to go back into the 5 hertz, what currently is the 5 hertz sampled data. And I believe the legato that we have being shipped to Georgia Tech samples at a higher rate. So that's very very exciting for us that we can get even faster sampling, because at times we find ourselves in very strong gradients, especially near the ice base as you sort of cross the ice ocean, or as you cross the near ice ocean boundary layer. So, right, Justin, you can move me forward one more time. And here's just an example of the post-processing that follows. So this is really just stepping through the steps that I listed before. And on this specific dive, what you find is basically by the end of the dive, there's these red stars with these square boxes. And what you see during that dive, we found conductivities down to 20 millisiemens per centimeter, which in the post-process data, this is sort of chopped off, but that's a salinity of something like 22 grams per kilogram. So very, very fresh. So that then requires us to go back into the 5 hertz data and investigate that specific time of, or a portion of the time series. So yeah, this is the post-processing pipeline that we're currently using, which I designed based off this RBR document that was released in 2017. And I believe that's it for me. I think I'm passing it back to you, Brittany.
Yep.
All right, thank you.
Yeah, thanks, Peter. I know we were up against the hour because there was a few technical difficulties at the beginning, so we'll just kind of roll through here just a little bit. Wanted to show you kind of what the outcome of all of the profiling and the corrections ends up being. So here's a typical, or not a typical, but here's a mission that we did in McMurdo Sound this past season. So this is the sea ice out here. The pink line is the driving route that we would take out to our sites from town. So this red line here is along a rift that is forming in the ice shelf. And that is a place where basically there's a basal fracture that's opening and the ice shelf is kind of getting ready to produce icebergs from this region. You can kind of see that some icebergs have actually kind of come out of this kind of tooth-shaped region here. So the individual colored lines are individual icefin dives, and they haven't been quite corrected. They actually do line up here, but this is just kind of a quick throwing our data into Google Earth view of what we were doing. So we're taking icefin and we basically explored 4 kilometers of this rift in the ice shelf. Next slide. So we'll just show you just a quick view of what it looks like. So here's our setup. So we're driving the vehicle, here's town. You can see the context of where the vehicle is and in the rift here. Then we're going to zoom in and you can see the different efforts from different thrusters. Here's some of the sonar data as we're going along underneath the rift. So you get to see some of the structures that we're seeing, and those structures all there relate to both the characteristics of the ice shelf. So this is the wall of the fracture, as well as the accreted or the frazzle ice that is produced in the ocean by supercooled water. So as we're driving along here, so this is our heading over here in the left, and our depth and altitude. Then another view of kind of the perspective that we're getting. So we drive a lot off of our sonar because we're often far enough away from the ice interface that we actually can't see the ice. But all of that ice in there, that kind of lumpy texture, is that frazzle ice that we showed earlier, the ice crystals that are forming in the water column and plating onto this ice structure at the bottom. So go ahead and go to the next slide. So then at the end of that dive, we kind of surveyed back and forth, but here's a subsection of the sonar stitched back together to give us the ice shelf structure. So we can see is that there's about a 40-meter wide section. So this is the whole rift area. So it's 40 meters wide here. It's much narrower at the far end. So we went from the from the tip where you could just see the fracture initiating all the way to where it was kind of leveled out at 40 meters. You can see this platelet ice infill, and so we can get the rate of frazzle ice production from the measures of the supercooling water and things like that. So the oceanographic column and the texture and the characteristics that we see on the bottom of the ice shelf are very related. And we're also really interested in things that allow us to get up close in proximity with those processes to understand everything from the boundary layer processes that are going on there to what's up in the ice. So next slide, please. So this is a 3-dimensional perspective on some of our CTD data. So what we're able to do, if you, if you want to run that again. So this is basically our initial cast with the vehicle. So we do this cast here. That's the vehicle dropping down from the surface down to the deeper water column, and we kind of hang and soak there, and then we bring it back up to the surface. This follows immediately after we've done a profile with our RBR CTD. So we do an RBR profile first, then we take the vehicle down and reproduce that with the CTD so that we have a good baseline. Then we come back up to the ice ocean surface, and these colored lines are basically distance from the ice, I think. But basically we kind of follow along. We do our survey. You can see here we kind of did zigzags back and forth across the rift, and then we did another downcast at the end and back up to the ice to kind of calibrate the data at the end and at the beginning of the dive, and then we take the vehicle back to the station. Next slide. So just a quick plot of what some of that data looks like, so we can look at it in temperature and salinity space. And basically, these ice crystals that I'm showing here on the left are the result of a lot of this water being below its in situ freezing point. So not only does it potentially confound the CTDs, but it also does that. And then you can kind of see mixing lines between the supercooled water and other components that we find in the McMurdo Sound. So basically just the real lesson is that it's a real challenge to do these proximity operations. But the neat thing about having a mobile platform is that it allows you to get up close and personal with the physics and to actually survey horizontally the same processes that we usually think of in a kind of vertical profile. So next slide. So what we're looking to do, oh man, we forgot to put the video in. So that's great. So what we're looking to do now, and actually I could probably just show that video here in a moment, is to be able to take Icefin under the grounding zone of glaciers in order to get up to the places where it is melting the most rapidly, at least in warm-based glaciers. So the image that I showed right at the very beginning of the talk of Thwaites Glacier and how it's collapsing, in order to understand why and how that's happening, we're trying to take the vehicle really close to places that we haven't been able to previously measure. And so being able to operate up close to the surface of the ice and in these very constrained geometries, places where the water column is incredibly shallow, allows us to measure, to get perspectives on this change in places that haven't been explored before. And so that's really the kind of horizon goal for what we're doing next. So if Matt wants to talk about the new plans, I can get the other video ready and I can show it there as well.
Yeah, I can just talk quickly. Basically, if you want to go to the next slide, Justin. Yeah, so you kind of saw from before, that's currently where we have the Neil Brown sensors up front. Fortunately, the Legato is only a little bit larger, and so it's going to go basically in the exact same place that our current CT is located. That helps because it's less things that I have to redesign, but also we're pretty familiar with kind of how the vehicle interacts with the sensor and the spot, where we can actually get the sensor to get those really fine boundary layer measurements. And so, yeah, there's just a few CAD models. We've been working with Eric and the team to make sure we have everything exactly where we want it. And then you can kind of see that last picture. I believe that is a glider in the calibration tank. And so what's cool about Icefin is we can send it in Pelican cases, and probably this whole module just in one case. So we'll be able to send basically the front third of the vehicle up to RBR to get calibrated. So yeah, hopefully that'll get done here probably by the end of the year. We should have all the design work and engineering done, and then we'll have it ready for the field work next year.
Yeah, so I don't know if there's any questions. I know we're probably a little bit past the end of the session, but Eric, I'm also happy to share my screen and show the other video if people are interested in some of the
thanks, Brittany. I mean, and team, this has been really, really wonderful, really fascinating to see. I see Brittany has been answering a couple questions along the way. There was one more that came at the end from Fred. He asked about how you get the vehicle out of the water, how you orient it to come back up the hole so it doesn't T-bone through.
Yeah, so basically the vehicle is, and we've thought a lot about this, the vehicle is neutrally buoyant, so it's actually pretty easy to just pull the tether basically back up the hole, but it also has kind of a halter, if you want to think of it that way, so that when we pull the tether up, it kind of pulls the tail towards the ice interface, and then we can get back in the hole that way.
Okay, I'm sure the first time you pulled it back through, you were quite relieved that it worked.
We have tested this to death and are still terrified of it, because anytime, nothing that we have ever planned to do with Icefin was an easy operations scenario or an easy retrieval scenario. You can't teach it to surface to get it back, right? If you're under even a few meters of ice, much less 600 meters. So thinking through that has been a team effort that everyone's been involved in.
Yeah, excellent. So I want to keep this open for questions. We'll stand by. One question that you responded to in the text, but I'd like to have a little bit more information because I think people that are watching this video might be interested, is a question that Miriam asked, which is how it's related to the work you're thinking about in Europa in terms of how frazzle ice forms, but also what kind of instrumentation you're looking at or thinking about.
Yeah, and while we're chatting about that, I just got a video of some of the work that we did at Thwaites Glacier. And so when we're talking about proximity operations, we mean centimeters to directly in contact with the ice, trying to see what's happening there. Yeah, so our interest in the planetary side of things is that, at least for right now and for the foreseeable future, everything that we know about the oceans of the outer solar system will be processed to us by its ice shelf. If you think about how the ice shelf is formed on Europa at the bottom of the ice is probably thickened and thin over time, but all of that is sourced from the ocean. And so that ocean sourcing process is very analogous to how we think marine ice and frazzle ice accretion is happening on Earth, and they're in very similar thermal conditions. So as we're studying the processes here with potentially analogous technology, then that is kind of the driver there, is to understand the physics of the system better here, to try to understand the scales of the problem, and then to then remap our heads to thinking about how that operates in a planetary context.
Okay, very good. I'm going to leave this open for anyone else that wants to pop in with questions by text or by audio. Okay, I'm going to take a moment to stop recording, but I want to thank Brittany and her team. Amazing science, really interesting technology, good photos, of course, and interesting data. So thank you very much, and we'll stick around. If anyone wants to chat afterwards, we're happy to host that.